Okay, we have somebody here who's throwing a ball, and this ball is going to be caught by a friend who is roughly the same height. Now, you probably should recognize this as a parabolic trajectory problem, and if you don't recognize it as such, then you actually probably won't be able to solve it. So the key here is recognizing that it's a problem involving parabolic motion, and then you have to know about what parabolic motion, the properties of it. So let's just remind ourselves of that. And we can do that by starting with drawing a parabola to show the motion of the ball. And this parabola, I didn't do a great job, but we know that the person who's catching it is roughly the same height. So we know that this is symmetric about some sort of center line here. So we got a couple questions to answer. One is, okay, first is the dotted line to sketch the path, and there we've got that here. The ball kind of looks like this, and this is supposed to be a parabola, even though I didn't do a great job of drawing it. Next, how long does it take for the ball to reach the peak height, in theory? And let's just kind of look at these questions. What's the peak height? So how long does it take to get up here? How far is this from probably from the initial level that it was at? When it's caught, what's the distance? Okay, what's the distance from here to this person right here? And indicate the velocity of the ball on the diagram in the moment that it's caught over here. And use an arrow and label the magnitude and direction of the arrow. Now that's probably the easiest one. I hope that you can recognize that when this leaves, heading in this direction, slowing down, vertical velocity at this point is nothing. And then it starts going down. So the vertical velocity, it starts out this direction, but then the vertical velocity reverses. So it falls down so that, again, if this is symmetrical, the velocity will be, excuse me, exactly the same as this one, but kind of this time down in that direction. Hold on, let me see if I can move this stuff here. Let me crunch it. Can I crunch it a little? Okay. So when the ball comes over here, the velocity will be actually the very same magnitude, 20 meters per second, but now this is going to be at 30 degrees below the horizon, because we know that it's at an angle of 30 degrees to the ground when it leaves. So this is 30 degrees here. So this is just, you can see the ball has just reversed its velocity from this to this at the very end of the trajectory. Now, you might recognize this as a 30, 60, 90 triangle. So you probably remember from high school that a 30, 60, 90 degree triangle has special properties. And that is that the hypotenuse is the ratio of the hypotenuse to one of the legs is 2 to 1 to the square root of 3. So that we have the sine of 30 degrees is equal to 1/2. Oh, I got my cat up here. Cat. Okay, now we're going to figure out how long. We've already done this. We've drawn the dotted line. How long does it take to reach the peak height? So, again, in order to do this, you need to know that the velocity going vertically at the peak height is nothing. So we look at our equations that are available to us, and you recall that this vertical situation is that of free fall. So in the free fall, all you have acting on the ball is the acceleration due to gravity. And in our case, we're going to use 10 meters per second squared. So we know that the gravity is pulling on this ball the whole time toward the Earth. So what that looks like on this graph, if we were to draw a set of axes, I'm going to pick from here upward. I'm going to pick an x-axis here and a y-axis here, and this is the plus y direction. This would be, of course, the minus y. And I know the acceleration due to gravity is a is negative 10 meters per second squared, and we know it's negative 10 because the negative indicates the negative y direction. Because we recall that acceleration is what we call a vector, so it has both magnitude, or amplitude, which is 10 meters per second squared, and direction, which is the negative y direction. Okay, how long does it take to reach the peak height in theory? So in theory, the only thing that is operating on in the y direction is the acceleration due to gravity. So if I were to draw a set of vectors, or break this velocity vector down into its components, we know it's 20 meters per second in that direction. That it consists of, now we can superimpose these, a velocity in the x direction and a velocity in the y direction. So this vector plus this vector equals this vector. That's what the superposition will give us, that you can add those together and get this net velocity. So velocity in the y direction is what we're concerned with. Okay, we know that the initial velocity in the y direction, VIY, is equal to it's equal to the sine of 30 degrees. Now recall that sine of this angle is equal to the opposite over the hypotenuse. So the sine of 30 times the hypotenuse, 20 meters per second, is equal to this component right here. So let me do that over here with this this diagram, because I'm kind of skipping something. So we know the sine of 30, the sine of this angle, is equal to 1 over 2. So therefore this 1 is equal to, 2 times the sine of 30. Now we know it's not necessarily 1 or 2. We just know these are ratios. I could alter this by multiplying this by any number. So I multiply by number b. What holds true is this ratio in this particular triangle, that the sine of this angle will always be this side over this, which will be, it could be 1b over 2b, but the b will drop out. So I know it's always 1/2. So I also know that the length of this is always going to be the hypotenuse times the sine of the angle. And if the hypotenuse is 2b, then it's just a b there. So it's 2b sine 30. If it's, instead of b, let's call it 10. Multiply everything by 10. 20, that becomes 10. 10 times 2 is 20. 10 times 1 is 10. 10 times the square root of 3. So this becomes 10 equals 20 times sine 30. I hope that makes sense. Anyway, so we know the velocity in the y direction is equal to 20 meters per second times sine 30. We've got that. Whoa, that's the initial velocity. Now, the equation that we're working with here is that the final velocity, v final, is equal to v initial plus at. And we know that the acceleration is this negative 10 meters per second squared. So we've got that, and we also know that the initial, or the final velocity, is 0 at this peak right here, because that's the final point that we're analyzing. We're trying to figure out, let me just remind you how long it takes to get to the peak height in theory. So now what we have is that 0 equals sine 30, so 1/2. 1/2 times 20 is 10 meters per second, minus this value, minus 10 meters per second squared times time. We don't know what the time is, that's what we're trying to find. So this, rearranging this equation becomes negative 10 meters per second equals negative 10 meters per second squared times time. And then if I divide both sides by 10 meters per second squared, negative, might as well, negative 10 meters per second squared, we can see that this drops out, and what we get here, the 10 drops out, the meters drop out, and we get basically one of the seconds drops out, and we get 1 second equals the time. Okay, with one significant figure. the time equals 1 second to get to that peak. Okay, 1 second. Okay, what is the peak height in theory? We'll try that in the next video.